All right, so now we're going to consider a new type of competing reaction. Or reactions, I suppose. So in this case, so we talked about before how we could have A go to B and then B go to C simultaneously. In this case, we're going to talk about parallel reactions. And in this case, we have A going to B, while simultaneously A may also go to C. And as engineers, we might be interested in reactions like this, where, for example, we might have some process of A going to B, and maybe B is our desired product, whereas C might be some undesirable product. Or even if it's not necessarily undesirable in and of itself, it's taking away from our reagent A going to B. So regardless, we don't like it. So you could imagine, 2A going to B while 3A go to C, or, 1A goes to 2B, or 1A goes to 3C, something like that. So we could have any number of, any order of these reactions. And also, we could, potentially have A and A going back and forth reversibly with B or irreversibly with C. But we're going to, for the rest of this lecture, we're going to talk about the simplest case, where for now, we'll just consider first order for both reactions, and we'll consider the irreversible case. And we'll also consider them to be elementary reactions. We'll also, the A going to B and A going to C don't necessarily need to have the same rate constants. So we'll consider the potential for different rate constants. Let's say A goes to B with some rate constant K1, while simultaneously A goes to C with a different rate constant K2. Let's say we'll start off with some amount of A naught, and we'll start off with no B or C. So, first question. Sketch what we expect. What we expect A of t to look like. And so we'll have a plot that looks like this, where we have A of t, and it goes as a function of time. So pause the video and sketch in your notes what you expect A to look like as a function of time. All right, so we might not necessarily know exactly what functional form we expect A of t to look like, but we know that we got to start off with some amount A naught. And since we have two irreversible reactions, eventually all of A is going to be depleted. So we know that A has got to start off with something. Its rate is probably going to be fastest at the beginning when we have the most of A, and then it's going to asymptote down to 0. So we could think about this either in terms of a number of moles of A or a concentration of A. So for now, let's think about them in terms of concentrations. I'm going to omit the normal brackets we talk about for describing concentrations, just so we can get through the lecture a little bit more quickly. So this is what we might expect A of t to look like as a function of time. So now another question. Which product, B or C, do we expect to get more of? Or which product, B or C, do we expect to gobble up more of the atoms that originally belonged to A? So pause the video and think about that. All right, so the answer is whichever of them had the higher rate constant, at least for first order reactions. So we'll, if K1 is much bigger than K2, then this reaction is going to happen many more times during the time period before which A gets totally depleted than this. So what do we expect B of T and C of T to ultimately look like? Well, we can at least, we might not know exactly what functional form we expect them to look like, but let's give B our color. Let's give B this blue color. We know B has to start at 0, and we know that its rate of production is probably highest at the beginning when the rate of depletion of A is highest. But eventually it's gonna asymptote to some value, and the amount of B that we ultimately end up getting once A is all depleted is, let's say, our B final. And we expect this to be proportional to the rate constant associated with this reaction. Simultaneously, we might get some C of T that looks like this, and it asymptotes to some value, which we could call C final, and that would be proportional to its rate constant. Now, think for just a moment about what we expect a constraint to be on C final and B final as they relate to A naught. We'll get to that later in the lecture. Okay, so next question. Using our rate laws, set up an ODE for dA dt. So pause the video and try to work that out. All right, so the answer will be dA dt is equal to, and we expect two contributions to dA dt. One contribution would be related to the first reaction of A going to B, and the second contribution will be from the reaction of A going to C. So we have depletion from two sources. So from our first source will be minus K1, and this is A going to B, so it's going to be minus K1 times A. And then from our second source, it's going to be minus K2 times A. Now, why are these A's here? Well, the A is still the reactant in both of these reactions. So that's why the ODE needs A's right here. But they're two different reactions, each with their own K's. So that's why they have their own K's here. We sum them because both of these are happening simultaneously, contributing to the overall rate of change of A with respect to time. All right. Now, here's the next question. What is A of T? Try to work this out on your own. Pause the video. All right, so we'll come back. What do we expect A of T to be? Well, there's a little trick that we can do to this equation before we get there. If we notice, we have A right here and A right here, so we can factor A out of this equation, and it could just be minus K1 plus K2, both of them times A, if we take this A, factor A out from both of these. And then in this case, well, K1 and K2, these are both just known constants that we could sort of just lump together and use as one term. And at that point, this equation becomes analogous to any of the first order ODEs that we've solved in the past, just with one single K in front of them. but we can just treat this sum of k's like we used to. So what would be the solution to that first order ODE? Well, in that case, it would just be A equals whatever our initial concentration A naught is, times e to the minus K1 plus K2 T. So this is sort of the standard form of our first order elementary reaction where we have an irreversible product, and this is the exponential decay that sort of has this characteristic shape of starting at something and then asymptoting towards zero. In this case, this would asymptote with a rate constant that is the sum of these two k's, because they're both acting in concert together to deplete A, both in a first order manner. This solution would be a lot trickier if one or both of these reactions were not first order, but for now we're dealing with first order reactions. Okay, so this is the solution of what we expect A of T to look like. All right, so moving on. Can we set up, next question is set up B of T with its rate law. So pause the video, take a moment to do that. All right, welcome back. We'll do dB dt. So first we're going for B of T, but we need a couple of steps first before we can get there. So let's do the first step of this will be just setting up what dB dt equals. So take a moment now and set up dB dt from its rate law. It'd be challenging to jump right away to the answer of B of T. So this is ultimately where we're going in this lecture, but for now we're just going to do dB dt, and then we'll solve this ODE. All right, welcome back. So now we have dB dt. Well, the rate of increase of B is just related to this one reaction of A going to B. So A going to B with rate constant K1. Well, B is a product in that reaction, so we get positive K1 times A. So A is a reactant, B is a product, so we get positive K1A. And it's first order, so we don't have any weird powers for A or anything like that. So this is our reaction. Now, can we solve this ODE? Well, it's a little bit tricky. We can't do separation of variables here because we sort of have two dependent variables, B, which is varying with time, and A, which is varying with time. So it'd be a little tricky just to plop down a solution to this ODE because we kind of have two dependent variables and then the independent variable time. So we can't do separation of variables quite yet. But what can we do? Can we solve this ODE? Spoiler alert, we can. And what do we know? Well, when we're solving ODEs, it's good to try to get something just in terms of our dependent variable and our independent variable. And that point, all we need to solve is that single ODE, and we don't need to worry about systems of ODEs. So is there anything that we have at our disposal to try to get this just in terms of B or T? We do. So we do, and we got it right here. So we got this A of T. So instead of having two goofy dependent variables, we can plop in this expression for time. And then at that point, all we have is things in terms of B's and T's. And that will give us what we need to solve this ODE. So when we make that substitution, we have A naught e to the minus K1 plus K2 T. And then at this point, we have just dB dt and things just in terms of a function of time. So we no longer have this goofy thing where we have both A's and B's and need to solve things as like a system of ODEs. So can we solve this differential equation? I'll give you a minute to try to do that, and then we'll return with the answer. All right, so we'll return. What do we have? Well, we can do separation of variables. So we can integrate. We'll have dB on the right-hand side, And then on the left-hand side, we'll bring the dt over here. So we have k1 a naught e to the minus k1 plus k2 t dt. And so right now we could worry about trying to put limits of integration on this. I'm actually going to hold off for just a moment on doing that, and we'll do this as an indefinite integral. We'll get a plus constant, and then we'll deal with that constant when we're trying to deal with the initial conditions. So what do we get on the left-hand side? Well, we just get b on the left-hand side, and then when we integrate the right-hand side, well, this stuff is just a constant, so we can pop out k1 a naught. If we integrate e to the negative something t, this plops out here as minus k1 plus k2, and then e to the minus k1 plus k2 t. And then, of course, we have our plus constant from having this as an indefinite integral. Okay, so we now have this expression here, but this expression we want to satisfy our initial conditions. So we'll use this constant here. We'll use to our initial condition. So what do we mean by our initial condition? Well, our initial condition is what b is at time equals 0. And in this case, b at time equals 0 was 0. So work out now what is that constant? What must that constant be in order to satisfy the initial condition? All right, so welcome back. We're now working out what this constant must be in order to satisfy our initial conditions. We can say 0 is equal to k1 a naught minus 1 over k1 plus k2 e to the, well, if t is 0, that's e to the 0, so this just becomes 1. So then we have plus constant here. So that means our constant must equal negative of whatever this term is. So negative of this term would just be positive. So now we can plop that back into our b expression. Now, if we notice, we'll have this sort of, this kind of common term out front. And we can kind of factor that out. So we end up getting a k1 a naught positive 1 over k1 plus k2. So times 1 minus e to the minus k1 plus k2 t. So this 1 here comes from the constant, which is a solution to this, to solving for constant in this case. This minus sign here came from the minus sign that belonged to this 1 over here when we got the indefinite form of our integral. So what does this look like? Well, if you were to plop this into your graphing calculator, you would end up with some function that looked like these curves that I was sketching up here, which start at 0 and then head up and asymptote towards some value. Now, question, what values might they asymptote towards? Well, we could sort of regroup our terms a little bit and think, question, what is b as t goes to infinity? So try to work that out. All right, well, what do we get? Well, as t goes to infinity, this term goes to 0, so we just get the constant left. And in that case, b infinity is equal to a naught k1 over k1 plus k2. So we can now, I regrouped these terms a little bit differently, and I did so to sort of reveal a concept we were kind of getting at earlier when we were talking at the plots. So the idea here is if we put in more a naught at the beginning, then we get more b as the b infinity as the reaction goes to completion. The idea here is we have competing rates. We have competing K1 and K2. So ultimately, it's the ratio of the particular K associated with B over to the overall rate at which A is being consumed in this case. So the overall rate of consumption of A is down here, and the instant or something that's proportional to the overall rate of consumption of A here, and then the rate of production of B is this term up here. So the ratio of B to the overall consumption of A is sort of accounted for in this term right here. So if we have competing K1 and K2, then this is related to the fraction that ends up as B. Okay, so now next question. What is C of T? And spoiler alert, we'll be able to do some tricks such that we won't need to solve this whole ODE again. All right, so welcome back. We had two tricks. There are two tricks for figuring out what C of T is. So trick number one is thinking about it. Well, if we were to set up the ODE for C, it would be dC dt is equal to plus K2 times A, right? Because A is the reactant for the C's reaction, only it has its own rate constant here. We can see that this is analogous to the rate to the dB dt that we had earlier, only a K2 instead of a K1. So we can just notice that, well, the form of the solution is basically going to be the same exact thing as what we got for B, but we're just going to have K2s instead of K1s. So we could notice there, in that case, that that it's analogous to our B of T solution. What's the other strategy? Well, the other strategy is that we know the atoms that belonged to A are conserved. So what does that mean? Well, we need to worry a little bit about stoichiometric coefficients, but if they're all, 1A goes to 1B, 1A goes to 1C, then our initial amount of A plus however much B we started with, plus however much C we started with, is going to equal however much A we have at some future time, plus however much B we have at that corresponding future time, plus however much C we have at that corresponding future time. So basically all the atoms that we started with have got to equal all the atoms that we ended up with. They're just rearranging themselves. We'd of course need to worry about stoichiometric coefficients if we had that in our original reaction, but we all had ones in our previous reactions. So for now, we won't need to worry about that. So what do we have here? Well, how does this help us with C of T? Well, we already have solutions for A of T and B of T, and of course we know what A naught is. So that just plops out the solution for C of T right there. And what does that end up being? Well, regardless of which strategy we go with for figuring out what C of T is, it turns out that C of T ends up being K2 over K1 plus K2 times A naught times 1 minus e to the negative K1 plus K2 T. So in this case, we still have the same shape, but instead of, but the term out front, this sort of fraction term, is different. Instead, the numerator, we have K2, with the idea is the amount of C produced is proportional to its rate in relation to the overall rate at which A was depleted. So how does getting B of T and getting C of T help us, right? Like, why do we even care about, productions of B of T and C of T? Well, we recalled at the beginning that we might have a case where B is our desired product and C is our undesired product. So in that case, we might want to reduce C as much as possible while having a high amount of B. So how can we quantify that? We had a couple of different strategies for quantifying how successful a reaction was. And one of the ways that we talked about how successful a reaction was selectivity. So we talked about selectivity in terms of two two different ways to think about it. We had a batch and an instantaneous selectivity. And the batch selectivity, we gave a tilde over it. And selectivities are always defined with one species with respect to another species. And usually they're products with respect to another product. So it's a desired product with respect to an undesired product. And in batches, that would be moles of B produced divided by moles of C. Moles of C produced. In our instantaneous selectivity, we don't put a tilde over, and it's still B with respect to C. And in this case, it's the net rate of B production divided by the net rate of C production. So, question is find these two selectivities. All right, so welcome back. All right, so first let's work out what the batch one would be. So S of B with respect to C. Well, in this case, we have an expression for B, moles of B produced at some future time, and we also have an expression for moles of C produced at some future time. So we can dig back into our notes. We can find those solutions that we so diligently worked out before. So for example, here was the B solution, and we could look at the analogous C solution. That was, right here at the top of the page here. So we can take their ratio. So our B solution was K1 over K1 plus K2 A naught 1 minus e to the minus K1 plus K2 T. And then C was K2 over K1 plus K2 A naught 1 minus e to the minus K1 plus K2 T. Can we simplify this expression? Can we simplify this expression a little bit? Well, yeah, we can actually. There's a whole bunch of stuff so these 1 over K1s plus K2s cancel out. The A naughts cancel out. Actually, these entire terms cancel out. And we're left here with just K1 over K2 for our selectivity, for our batch selectivity. All right, now, can we work out a similar expression for our instantaneous selectivity? So pause the video and try to work that out. Well, yes, we can. So we can just plug in the rate laws for the two. So the net rate of B production, net rate of C production. There's only really one reaction involved in these things, so we can work it out. So the instantaneous production of B is just K1 times whatever the instantaneous amount of A is. So this is from its rate law. And the production of C is K2 times whatever the concentration of A is. So these A's actually cancel out. And we end up getting K1 over K2 again. So it turns out, just by chance, that this is the case, that these are the same, the batch versus the instantaneous selectivity. That's not always going to be the case. So not always the same. And think for a moment about what some cases might be to cause these two things to not be the same. So under what circumstances might we not have the same instantaneous or batch selectivity? So the cases that might cause them to not be the same might be cases if they were no longer first order reactions or no longer elementary reactions. And in that case, we'd have different powers. So A would be affecting each of these things differently, so the A's wouldn't cancel out. If we had not first order reactions, we might have an A squared up here, but just an A down here. And then because A would be varying as a function of time, this selectivity would be varying as a function of time. Also, these functions might not perfectly nicely cancel out if they both weren't first order. So we'd have different functional forms here. So we'd get some goofy function of time here for the batch selectivity as well. And those might not be the same as each other. So we'll get more into that in the future. All right, now one last thing is what can we do to affect selectivity, right? We're engineers. We want to optimize something. We want to get as generally as high of a selectivity as possible. So think for a moment, what can we do to affect selectivities? And we could think of either affecting the instantaneous selectivity or the batch selectivity. So could we change the duration that we let the reaction go on for? Can we change the concentration of A? This would be of A. Can we change temp? Which of these would affect it? Well, so duration might work for other reactions, but not for first order reactions, right? So we just determined that the selectivities are independent of time. So whether we let this reaction go for 1 millisecond or 1 hour or whatever, that's not going to affect the selectivity at all because our selectivities were independent of time. Furthermore, we noticed that that the initial concentrations canceled out in the selectivities as well. So in this case, not for first order as well for concentrations. All right, so spoiler alert, what's the last thing? Temperature. Do we expect temperature to do so? Yes. So we expect temperature to affect Ks, and by adjusting the ratio of K1 to K2, then we can ultimately get our selectivity to change. So can we work out what we expect that to be? So question, using the Arrhenius law, derive an expression for the batch selectivity as a function of temperature. All right, so pause the video and take a moment to do that. All right, so welcome back. So the answer to that, well, if we can do the Arrhenius law, we know it's K1 over K2 is our selectivity. And we can just substitute in the Arrhenius law for each of these Ks. So we'll make distinctions between the pre-exponential factors, A1 times e to the minus activation energy for 1 times RT. So we'll keep in mind this 1 here, so this A1, this A is not the concentration of our reagent A or anything like that. This A was just the factor out in front of our exponential in our Arrhenius law. So we're making a distinction here between the pre-exponential factor A and things up here like concentrations of A or initial concentrations of A. So sorry to overload notation. This A is different from concentrations of A in terms of moles. We can also plug in this stuff for A2, for K2. So we expect K2 to potentially have a different pre-exponential factor than 1, and also it could have a different activation energy than reaction 1. So we recall that temperature has an influence on this e to the minus activation energy over RT term in the Arrhenius law, and ultimately an influence on the rate constant for K's rate law. These should be lowercase k's. So because the pre-exponential factors are going to be different for K1 and K2, possibly, and the activation energies are probably going to be different for K1 and K2, this numerator is going to grow and shrink at a different rate with temperature than the denominator is going to grow or shrink with a increase or decrease in temperature. So ultimately, we expect that the ratio of K1 to K2 will change as a function of temperature. And as engineers, we can turn the thermostat on our reactor up or down to favor production of our desired product over our undesired product. So let's do a little bit of simplifying to this expression. And so we can do A1 divided by A2. If we have this ratio of exponentials, we can combine them together into a single exponential. And this would be exponential of So we can sort of combine these two e to the minus things whatever into a single e to the minus difference of activation energies over RT. So the based on the differences in the activation energy, we can expect to affect the ratio of Ks. And we can influence the degree to which this difference of activation energies influences this overall ratio by turning up and down the temperature on our reactor. So question, if the activation energy for our first reaction associated with K1 is greater than the activation energy of our second reaction associated with K2 is if the first activation energy is greater than the second activation energy, how should we adjust our temperature in order to favor our desired product, K1? So pause the video now and think about that. So how do we expect if our first activation energy is greater than our second activation energy, how should we adjust temperature? Well, in this case, we want we should increase the temperature to favor K1 over K2, or at least to get K1 to be higher. K1 will grow at a faster rate than K2 in that case. So by raising temperature, what effect would that have? Well, our selectivity is proportional to the e to the negative thing over temperature. So if the contents of our exponential is going to be negative, and there's really nothing we can do about that as if this term is bigger than this term, because we have this minus sign out here. So if that's the case, there's nothing we can really do about trying to make this exponential of a positive thing. So if we're going to have a negative number in here, we want that negative number to be as small as possible, to have this overall term to be as big as possible. So by raising temperature, we can decrease the magnitude of this negative number inside the exponential, and then that will make s as big as possible. Alternatively, we could think about the Maxwell-Boltzmann distribution, and we can sort of think about physically what's going on with atoms and molecules. So if we talk about the Maxwell-Boltzmann distribution, that was a function of how many molecules have a particular kinetic energy. So in this case, let's sketch two of these. One at a low temp, and then we'll sketch another at a high temp over here. So this is B. This is number of molecules as a function of kinetic energy. So we'll have some distribution that looks like this. Let's say our activation energy for, and we said that our activation energy for our desired product just unfortunately happened to be higher than our activation energy for our undesired product. So in this case, let's say EA1 is right here, and let's say that EA2 is right here. Well, if we look at the number of molecules in our distribution, most of these molecules have sufficient energy to make reaction 2 happen, whereas only a couple have sufficient kinetic energy to make reaction 1 happen. Conversely, if we increase the overall temperature at which our reaction is happening, I'm going to need to extend my axis a little bit here. So in that case, if we increase the overall temperature at which our reaction's happening, we can now push the bulk of the molecules to be above both the activation energy for our undesired and our desired one. So in the first case, we had all of these molecules that could proceed with this reaction but couldn't proceed with this one. In this case, we have only a few molecules that that can proceed with this reaction, whereas most of the molecules are above the activation energy threshold for both reactions to occur. So we can think of raising temperature as affecting the proportion which is in between the two activation energies. And if we want product 1, then we want to basically push the entire distribution to be above both activation energies. So thanks for watching, and we'll proceed next time or in the future thinking about how these selectivities and our ability to control selectivity and our analysis of competing reactions in parallel would change if we were not dealing with simply first order reactions. Thanks.